Well, welcome. How's everybody doing? Great. Oh, thank you. Appreciate that. Ready to hear about Kubernetes and some machine learning? Great. Well, we got Joy and Lockie from Microsoft. Please give them a warm welcome.
Thank you. I think you're in for a real treat in this session, and you're going to hear a wonderful story of both Joy and myself and our journey to learning about machine learning on Kubernetes. So why don't we get into it? So my name is Lachlan. I'm down the bottom there, and this is my esteemed colleague, Joy. We both are from Microsoft, Azure Containers, and Joy, you could...
Thank you, everybody. My name is Joy. I'm a solution architect from the Microsoft AI platform team. So I work with data scientists a lot.
Okay, so we're going to get into this. This is a story and a journey about us both. And before we get into the nuts and bolts of the story, you need to learn about who we are individually, and that gives you context about this story. So, Joy, why don't you tell us who you are in this story?
Sure. So I'm a solution architect that works with a team of data scientists and data engineers on a daily basis, building models, training models every day. And we've been using Kubernetes as the underlying orchestrator for a lot of our machine learning and deep learning workloads. So we've been working with Lachy a lot on optimizing our deep learning workloads performance on top of Kubernetes.
Okay, so Joy represents the data scientist in this story. Myself, I'm the infrastructure SRE, so I have deep Kubernetes knowledge. I have a lot of knowledge of how the cloud works and how to get the best experience out of the infrastructure on the cloud. But I have little to no experience with machine learning, so you're going to have to see this through my eyes as well as Joy's eyes. So in this story, we're really the intersection here. Joy came to me and said, hey, do you have anybody on the team that can help us in Microsoft Research actually get the best out of Kubernetes and the best out of what we're trying to do with our machine learning on Kubernetes? And all the while she said, also, I'd like to learn about Kubernetes. So it was kind of this exchange in this Venn diagram of knowledge where Joy taught me all the nomenclature in the machine learning, which I was once scared of. Hopefully I can break down those walls. And I helped Joy and her team understand how Kubernetes ran and how to get the best out of Kubernetes. So that is our story. Who here in this room identifies as a data scientist? Have any data scientists? Fantastic. I'm hoping there's something in here for you. And infrastructure engineers? Fantastic. All right. So I'm going to try and represent the infrastructure people in this room in getting all that scary nomenclature and naming that machine learning folks work with. And Joy's going to explain things in terms that we can understand, because half of my challenge was understanding what they were talking about and mapping it to what I knew. So why is this important? You know, the title is Democratizing. So there are a lot of folks coming to us at Microsoft and Azure and saying, we want to start getting a foot into deep learning on Azure. How can we actually take advantage of the infrastructure to do distributed training? So when we actually take a look at the state of the tooling in the environment, we have a wonderful platform in Kubernetes. Is my mic going? Is it just me skipping? It's the mic. Okay, good. I'll keep going until something happens. Okay, so we have the right platform in Kubernetes, and we have the right tools and libraries in things like TensorFlow and PyTorch to actually get the job done. So coming to this intersection and actually going through this journey together was extremely fruitful for us both, and I think we have a lot to share in this. So the knowledge out there today, if you go and take a look at TensorFlow, you look at the documentation, there's great documentation on how to get started on single nodes, but I think when it comes to distributed, which is really what you want to get to this, what I call the oil slick, an inch deep and a mile wide. You want to have lots of nodes to compute, and you want to get through training models, getting to serving models on the fastest rate of return that you can get. So when you actually take a look at the docs out there, there's not much in the distributed version of this, and that's what Joy's going to take us through. The nomenclature is tough, so when data scientists come and say to the infrastructure folks, I need to move this gradient to a parameter server in this region, and please make sure that nickel works. What is this? I don't even know what any of these things. We're going to go through that. When we looked at the docs, most of them were out of date because things are moving really fast, and I think my mic might be ready to be changed. So shall I tap dance? No worries. Don't worry, we're all in tech. These things happen, right? No? Just me? Okay. And the infrastructure is changing really quickly, not only in Kubernetes, but if you take a look at things like TensorFlow, each release is packed with more and more features to support these types of workloads. So let's get started here. But before we get into the nuts and bolts of what we did and what we learned, Joy is actually going to take us through distributed deep learning architectures, and I think what this will represent for the infrastructure engineers is how does this map to mental models, containers, pods running on nodes. Take it away, Joy.
Thank you, Lucky. So before we deep dive into a lot of the nitty-gritty details of doing distributed deep learning on top of Kubernetes, I just wanted to provide some quick context on the basic distributed training architecture. So one very popular way of doing distributed deep learning training across multiple nodes, across multiple GPUs, is called data parallelism. So how this works is basically you place a copy of your deep neural net model inside every single GPU device you have got. And then you feed a mini batch of your entire training data set, one batch at a time, into every single GPU you have. And each GPU just trains the model using that mini batch of the data it has. And at the end of that iteration, each GPU will have a set of gradients, which is basically the delta of the parameters of the model that need to be updated. It will have a set of gradients, and it will send that gradients either to a centralized parameter server for global gradient aggregation and parameter updates, or the GPUs can directly talk to one another among themselves for the gradient exchange, synchronization, and update.
Yeah, I think the main things that I took away from learning here was parameters equals variables for the model,
yep,
and gradient equals delta, so changes post-train. So in an infrastructure, okay, so I have a delta post-train, I need to transfer that back to redistribute it to all the models that live inside all the GPUs. So thank you.
So the second way of doing distributed training is called model parallelism. So this happens when you have a deep neural net model that is too big to fit into one single GPU. And this is often a scenario when you're doing large-scale natural language processing, when you have really large LSTM models or like big neural machine translation models. What you can do then is you need to divide your big global model into a number of submodels, and each worker will just work on the submodel, and then obviously they all need to work with each other to train the global model. And this is a typical distributed TensorFlow training architecture. If you have done distributed TensorFlow training, you must have seen this diagram a lot. So here, as you can see, typically you will have one or more parameter servers sitting at the top, and then you can have multiple workers. Each can have one or more GPUs. One thing with TensorFlow, especially if you have each worker has multiple GPUs, to optimize the network communication and network bandwidth here, each worker will do a per node level local gradient aggregation first before communicating to the parameter server. So only the per node level aggregated gradients get sent to the parameter server. This way, it reduces the network communication cost a little bit, and also reduces the parameter server, the work that parameter server needs to do as well.
All right, so I want to dive into some tooling to actually make distributed deep learning work on Kubernetes, and actually take you through some different use cases. So today in the open source community on top of Kubernetes, there's a tool called Kubeflow. Kubeflow is a set of packages that are pluggable. So you're not bound to any one way of doing things, but inside Kubeflow, out of the box in the early releases, you could do Jupyter Hub. Jupyter Hub gives away, basically I call it Google Docs for machine learning writing the machine learning models. So it's a way to collaborate on the creation of models between data scientists. And then you could do TensorFlow training and serving. And we just spoke about distributed training there a little bit. In more recent releases, things are pluggable. So if you're not using TensorFlow, you're using PyTorch or Caffe or something else. And one thing that we wanted to do with this session was make everything hands-on. Those links are there and they'll be in the slide deck at the end as well. But we actually have a step-by-step lab for actually working through Kubeflow on your own and going from building a model on your own Docker daemon for Docker for Mac or Docker for Windows and getting that up into a Kubernetes distributed learning. There's also another tool that is open source by the Microsoft research folks called Deep Learning Workspace, and that's a very UI-driven user experience where a user doesn't need to know anything about Kubernetes, and they can go in and actually train and run their models. So there's two sets of tools. The interesting thing with TensorFlow is what's actually happened in the Kubernetes community is they've created a custom resource. So if you've attended any of the custom resource talks whilst at DockerCon, there is a simple way to extend Kubernetes to make it your own, and that's through custom resources. So there is this custom resource here called a TF job. And TF job, this is the custom resource definition. There is a controller that accompanies this definition, and its job is to watch and implement distributed TensorFlow jobs on top of Kubernetes. So, but as we can see in here, and given what Joy has told us, under the spec section there, about 4 lines down, you can see replica sets, replicas. We have a TF replica type of master. And on this next slide, we also have workers and parameter servers. So this gives you a very lightweight way to define distributed TensorFlow jobs and have a controller that knows how to implement these inside Kubernetes. So with this one file, you can apply this to Kubernetes, and TF job controller will pick it up and understand how to run it on Kubernetes without you having to know the knowledge. The other thing that is displayed there is the GPU. So we're asking for 1 GPU for the worker nodes there as well. One of the other things that we'd like to do, and I'll show you some hands-on demos after this as well, is to try and create a more simple experience for data scientists. Now, understanding that YAML file in unto itself is a task, and for a data scientist to understand all the fields that go into creating that task is somewhat onerous. We actually work with the team internally, and we created this project. It's still called MetaML. We might rename it, but it's experimental. But the way that MetaML works is you can see there on line 50, there's an @train class decorator there. So this is inside your machine learning model in Python. What we're actually saying is, without leaving your source code, we can actually compile and create this thing without you having to know the YAML file implementation as well. So on line 52, we're saying the architecture is distributed training. I want 1 PS and I want 3 workers, and I'd like a tensor board attached to that so that I can actually introspect the running of the model. So this is just some way we're actually experimenting with actually moving the needle up, and this works on a project called Metaparticle by Brendan Burns. So if you're interested in more about that, feel free to come and ask me. It's all open source as well, and we have some labs to walk you through that. So before I get into the demos, there is nothing here proprietary to Microsoft. This is all open source, and the abstraction is Kubernetes. So all you're going to need to run this up at home or at your own leisure is a Kubernetes cluster. Doesn't matter how you get that. Docker for Mac, Docker for Windows is just fine. AKS, GKE, EKS. The abstraction there is Kubernetes. If you can supply GPU nodes, that is a benefit, obviously, if you're doing your training in GPUs. You install Kubeflow, and then you run that distributed training job. And as I said, there's detailed instructions on this repository that you can go check out for yourself. So demo time. Okay, so hopefully everybody can see this. In the top screen, actually, what I have is a kubectl running, just displaying the pods in the default namespace, which we have none. In this middle, I'm actually going to spin up a container and run my data set through this workload that I've built in a container here. And let me just get this up and running. Okay. Kubeflow demos. So the first demo here, and this is taken straight from that open source repository. So I'm just going to run this demo. And what this demo is going to do is create that distributed TensorFlow job that I showed in the slides. Up the top, you can actually see the master, the PS come up, and the worker. So the TensorFlow operator, the TensorFlow controller, has picked that up and started that distributed TensorFlow job with one command there. And now I'm just attaching a tensor board to that. And for those of you who haven't worked with TensorFlow, a board allows you to actually introspect what's happening while that job is being processed. So what I can do here, just to close the loop, is do a kubectl port forward. So I want to attach to the tensor board because it's a web UI. And I'm just going to pipe the tensor board through to my machine. I'm going to open another tab here and hit the tensor board. Right, so what you can see here is I'm actually training against the MNIST data set, and that's actually just some handwritten numbers and letters. So this is actually the training job running in distributed mode right now. I've split the data set between train and test, and you can actually see that. Now, I did all that with one command. So this is already getting much easier. When Joy and I did this 6 months ago, it was much more complex. The final thing I wanted to show here is I actually have the Storage Explorer. So this is using Kubernetes under the hood here. I'm just going to refresh it. So you can actually see all my binary data from that run is all aggregated into persistent storage and stored on Azure files at the moment. So everything is persisted to cloud storage, which it doesn't matter where you get that cloud storage, it will work. I wanted to show just a little more complex of a demo here. I just showed a distributed training. One common thing that data scientists like to do is actually do hyperparameter sweeps. So actually run a matrix of all the parameters at the same time to determine which one yields the highest accuracy. So if you're trying to identify an image as a dog, you want to make sure that you're at 98% accuracy on that. So what I'm going to do is another demo here. And what this is going to do is install a hyperparameter sweep using Helm under the hood, but it's going to be using the same TF job. So let me just show you this here. So what we can see is actually all these new pods running up to run that distributed hyperparameter sweep. And I have a tensor board here coming up again to which I can introspect. And this specific model, I will go back here and grab once this tensor board actually starts up, I should be able to port forward to it. Okay, so it's up and running, and I should be able to just refresh this page. And again, so you can see over here on the left, here's all the runs, and these are all the parameters for this set of models. So we can see I have different learning rates and different hidden layers. But what this model is being trained with is trying to paint a work of art from Van Gogh. So you'll see as it steps through the training data, you will actually see this Van Gogh. I will leave until the end and we can come back and take a look at it. But here is another simple way with a single command that we can actually run this and make it very lightweight for data scientists alike to actually have access to this. I think finally, actually I will pause my demos here and we'll go back to the slides. If we have time for one more demo at the end, we can do that. Okay. So after we had this set up, we were able to go back to Joy, and Joy actually ran a bunch of benchmarks. So we're going to share how distributed training actually performs and scales. So I'll hand it back over to Joy.
Thank you, Lucky. So we actually did do some benchmark testing on Azure just to see like what are the options, how we tune different options and knobs to really optimize the deep learning training workloads here on top of Kubernetes. So before I share the results, just to go over the training environment quickly, we have two worker nodes. Each has 4 GPU Tesla K TGPUs. We also have one parameter server that is just a CPU server, since the parameter server's job doesn't really do any actual model training itself. It just does the gradient aggregation and parameter update. And we did use the latest TensorFlow version 1.8, and also the benchmark is from the upstream TensorFlow benchmark as well, with the real ImageNet dataset, not the synthetic data here. So before going into the distributed performance, let's just take a quick look at how the model training performs on a single pod with multiple GPUs. As you can see here, on a single pod, actually the model scales pretty well and pretty linearly as well. Here I'm just showing the ResNet 50 as an example, but we've actually tested a lot of different neural nets, and it turned out that they all scale from 1 GPU to 2 GPUs to 4 GPUs pretty nicely, and you do get that linear scalability here, and all the GPUs are fully saturated, which is a good thing. That means you're not wasting your GPU resources. And then going into the distributed training world, just to go over the topology here really quickly, we have one parameter server and 2 workers, and we use the async variable update mode. Async mode basically enables your each worker to directly communicate to the parameter server anytime, and it doesn't need to wait for the rest of the workers to all complete their mini batch of the training before the worker can move on to the next batch. So this really helps if you have some slow network bandwidth. But one thing to call out is also if you're doing async, watch out for your speed to accuracy, because sometimes this async mode means your parameter server can get a stale model from a super slow worker that might be really behind the other workers, and that might hurt your model accuracy, and you can see your model accuracy performance go up and down a little bit. So that's a tricky choice to make sometimes, doing sync or async variable update during your training. And also, we didn't use any fancy InfiniBand. We just use our normal Ethernet and using the GPRC protocol. So here are some interesting results we've observed when scaling out to 2 nodes versus doing a single pod training. As you can see here is obviously now not all models are behaving the same anymore. They all actually behave pretty differently. From the left-hand side here, you can see GoogleNet and Inception v3 actually scale better than the other models. We get about 1.7 speed up comparing to the single node training. And then ResNet, we're getting only about 1.5 speed up, and down at on the right-hand side there, VGG, which is actually a pretty heavy model there, it doesn't really scale at all. You're not getting, we didn't get too much of performance gain scaling out to 2 nodes compared to the single node training.
Yeah, I think that data was quite a revelation to me, because I just thought I could throw more hardware at the problem and scale out the Kubernetes cluster. But you can see with depending on the model and how you're training it, you actually don't get linear scalability or even anything close to it. So this kind of begets our further investigation.
Yeah. So to dive deeper into why these models are all behaving differently, it turned out it actually came down to one single key characteristic of the model, which is the compute to communication ratio of your model. The compute really refers to the computation cost of your model, like how much GPU power it really takes for your model to get trained. And the communication factor there refers to just like how big your model is, how many parameters your model has. And the ratio of the two really is the deciding factor here, especially if you have limited network bandwidth, physical network, limited network bandwidth. The higher the ratio is, the better your model can scale, and this actually aligns with the testing results we find as well. there you can see GoogleNet has the highest ratio, and that's why we also observed it scales the best there. We got about 1.7 speed up. Versus VGG there, VGGNet, to give you some concrete numbers, VGG 16 model is a really big model. It has about 138 million parameters. So that's why it is actually very difficult to scale over multiple nodes. Compared to ResNet 50, it has about 20 million parameters. And GoogleNet, the one that scales the best, it only has about 5 million parameters. So that's why it is actually very different. All these models are behaving very differently.
So without any intervention, the best we could get was 1.69 scaling factor.
Yes.
And the worst was 1.06.
Some other observations we also observed is also obviously two key things that would decide how much linear scalability you get, which is the model itself, and also how much network bandwidth you have. Obviously, if you do have InfiniBand RDMA, that would help. And if you are bottlenecked by the network bandwidth, that means a lot of the time you will observe your GPUs are basically just sitting there idle, waiting for the network communication to happen. And so when that happens, you're basically wasting a lot of the GPU resources. And the other thing that I wanted to call out is the worker to parameter ratio. It is actually also a tricky design decision to make. It is not always the case that you can scale out to, you can add more parameter servers and help with your performance. Sometimes by adding more parameter servers, you incur more network communication costs, and so sometimes it can even hurt the model performance there. So how can we do better? It turned out basically there's a lot of things we can improve on both sides of the world. There's technique on the machine learning side of the world, and there's techniques on the infrastructure side of the world that can really help with distributed training. One key really useful framework I wanted to call out on the machine learning side of the world is Harrowwatt, and that is Uber's open source distributed deep learning framework for TensorFlow, Keras, and PyTorch. So what this does is, this is actually a standalone Python package that can work on top of your TensorFlow, and it really addresses the two key problems that we just went through. Number one is the network bandwidth bottleneck, and number two is the tricky decision of deciding how many parameters you should have, how many workers you should have. So what this uses is it really leverages a nice algorithm called ring or reduce, which is very efficient at inter-node or intranode GPU communication, and it uses this ring or reduce for the GPUs to directly communicate one another among themselves without needing to talk to a centralized parameter server anymore. So the GPUs can directly communicate among themselves using this highly efficient algorithm called ring reduce. And then you don't need a parameter server anymore. You don't need to decide how many parameter server you need to have. And also, it leverages Nickel and Nickel 2 libraries from NVIDIA for doing a lot of the GPU to GPU communication, utilizing the underlying GPU topology you have within one server and across multiple servers as well. So it really reduces a lot of the network communication overhead there. So as a result,
I think it's worth mentioning it's just a drop-in framework, so you don't have to actually change your model. You just drop it straight into TensorFlow if you're using TensorFlow or PyTorch.
So as a result, you can see a much better linear scalability here when you scale out to multiple nodes. You get much better predictability of how well your model can scale, and that way you can design how many workers you need exactly in a much easier way. And we also did verify this in our own cluster as well. The same cluster we used for testing the initial default TensorFlow distributed training benchmark. We used the same cluster for testing out this HelloWorld. We got really some immediate performance improvement using HelloWorld. Now you can see for most of the small and mid-sized neural nets there, we achieved about over 1.9 speed up. In terms of the linear scalability here for most of the neural nets there. The only, like even ResNet 156 got about 1.5 speed up, and VGG is slightly improved as well. But those are like really big models, and those models are literally bound by the physical network bandwidth there. And just to share, like, the network bandwidth we had is only about like 4.5 gig, so it's nothing fancy. It doesn't really use any RDMA. So typically to train those large neural nets, you will need, like if you do need to train a VGG16 large neural net, you would need to consider using an RDMA-enabled network there. So on the infrastructure side, there are also some great tools you can leverage to boost your model training performance. One key thing to call out here is the FreeFlow CNI network plugin from Microsoft Research. And by the way, we just open sourced this project about a few days ago. You can all use it, and we use it a lot internally. Whenever we do distributed machine learning, deep learning training, because this FreeFlow plugin really helps with the network bandwidth communication. It really speeds up your container overlay network communication to the same level of performance, network performance you can get on the host machine. And it does support both RDMA and TCP, so even if you don't have RDMA, if InfiniBand, you just have TCP, you can still benefit from using this plugin. And also it reduces your CPU overhead a lot, so your CPU doesn't have to do a lot of the network communication transfer work there. It's very easy to deploy into a Kubernetes cluster. Basically, all you need is just to deploy a set of daemon set, and then add 2 environment variables into your pod definition, and that's it. We've got detailed instructions there shared at the GitHub link there. You can go in and check out. This really boosted a lot of our container-to-container network communication, which by default often has a lot of overhead compared to the host-to-host network communication. The other very useful tool, which is also from Microsoft Research, is the GPU resource scheduler. This helps you and enables you to define a pod with not just how many GPU you need, but also how many GPUs you need with how much memory, and also do you need a set of GPUs that are interconnected with by NVLink. These are also super important when you do cross GPU deep learning training as well. And then finally, on switching back to the machine learning side of the world, I do want to call out there's this Fast AI about 2 months ago just published their bunch of techniques and their benchmark results on the Stanford Dawn Bench project for training. They achieved training ImageNet within 3 hours for just about $25. And they did use a lot of very neat techniques on the machine learning side of the world, including like superconvergence and progressive resizing, which is basically you can start your neural net training by feeding in some smaller images at the beginning of the training. which actually makes very intuitive sense as well. Is like when you start training your neural net, just to enable your neural net to learn the difference between a cat and a dog, you don't really need to give it some big high-res images. And you can just feed it some small images, and it can tell the difference between a cat and dog very easily. But when you train further on, and you want your neural net model to learn the difference between every breed of dog and every breed of cat, then yes, you do need to give it a larger image, high-res images, so it can learn the difference between different breeds of dog. So that way, actually, you can pump through more images into your neural net and get much faster training speed. And that's how the Fast AI guys actually achieved training their ImageNet in 3 hours. And one key thing is they did all of this actually just on a single node. They did all of this on a single node with 8 V100 GPUs. And that's something that is actually pretty amazing, because if you look back, around this time last year, Facebook also published a paper they achieved training ImageNet within 1 hour. But if you look into the paper, that was actually using 256 GPUs across a lot of machines, and they had a pretty fast network, about 50 gig network as well. But all of this, you can just do on one single node. So this is something worth calling out. And there are a lot of papers there, and if you're interested, check it out. I think all of these techniques resonate really well with the theme of our session here, which is all about democratizing machine learning using like very accessible, free, open source tools and techniques out there that can really help you do your machine learning training very cheap and very fast. Back to you, Lucky.
Thank you, Joy. So we've taken a look at these architectures, we've taken a look at the tools out there, showed you some benchmarks, so some things to look for and maybe some ways you can improve on them. And we also know some tooling and libraries out there. So we've given all the resources. I'd encourage you to come and talk to us. We only have a couple of minutes at the end of this, but we can be in the hallway out there. I'm also going to be on the Cloud Native booth later this afternoon, so if you're interested, swing by. You can ask us anything about all this, but I encourage you to continue the conversation on Twitter and reach out and make a friend to a data scientist if you're an infrastructure engineer, and likewise, because working together you can actually make some marked improvements on the way that these things work. And we encourage you to come and help us in the community to make this more accessible. Thanks for joining.